Chapter 7, second part. So, from the previous lecture, we defined directed animal on the square lattice. We showed that it was very easy to solve once you know Heaps genetic function, because directed animal on square lattice are in bijection with some pyramids, in fact strict pyramids, and extension directed animal on a triangular lattice, where the northeast step is lowered, then it's in bijection with pyramid, which are counted by half of 2 and 2 then. And then we begin to understand what means the thermodynamic limit in statistical mechanics from the pure combinatorial point of view. So the most simple example was a gas model. You put some particle in red on this segment line with endpoints, so that two particles are not connected by an edge. And the partition function is a polynomial which enumerates all such configuration. So if you prefer, you can transform the point into dimers. You get a trivial ellipse of dimers on the segment of length n plus 1. It should be Zn equal Fn plus 1 here. And so the partition function is a Fibonacci polynomial when you replace t by minus t. And so thermodynamic limit means you take this polynomial, take power 1 over n, and take the limit when n go to infinity. So to understand what it means in terms of generating function, taking the 1 over n, power 1 over n of a polynomial, it's good to take the logarithm. And from the logarithmic lemma, logarithm of the partition function, it's good instead of taking logarithm of this polynomial, it's 1 over n logarithm of the inverse. We can put the inverse polynomial. So it's just minus the logarithm. And then you can better understand the thermodynamical limit, because this is a generating function for pyramids. And 1 over n means you are taking the average generating function of all pyramids. The pyramid with maximal p is 1, 2, 3, 4. For each integer I, there is a pyramid. There is n points. So you are taking the average of all generating functions for all pyramids, which maximal p is fixed on the number I. And then there was a small drawing. You see, this is all possible pyramid at point I. And then when n go to infinity, if you fix k, so this segment is going to be very, very big. And if you take the first term of the derivative function of pyramids center on the point I, this will be independent. All this pyramid will have the first term will have all the same, will have all the same. So we understand that going to the limit means you cancel this border effect, and at the limit you get the generating function for all pyramids with no condition on the bounds. So at the limit you have interpreted this theorem, the minus rho of minus t, where rho is the density, it's called in physics the density of the gas. If you take minus rho of minus a, this is the generating function of pyramid on Z up to a translation. And so we have seen that pyramids, in fact, are in bijection with directed animal. So this is also the directed animal give an interpretation of the coefficient of the density for the gas in one dimension. So this is very easy. When you have only one-dimensional gas, the most difficult problem is to have two-dimensional gas. And the special model have been solved by Baxter, the hard hexagonal model. It's not solved for square lattice or rectangular lattice, only for the triangular lattice. So you take a finite domain, the same idea as for gas in one dimension or gas in two dimensions. You take any finite domain D of the triangular lattice, you put some point independent set in graph theory, means trivial ellipse in Heaps theory, means that this point in black, you choose, they are not connected by an edge, and you take the polynomial which enumerate all such configuration of point, 2 by 2, not connected by an edge, in the finite domain D. And then you have to take the limit of this polynomial power 1 over the number of points of the domain. Once you get Z, then the density, rho, is a t times derivative of logarithm of this. This is defined by physicists. Yes, Amri?
What is the interpretation of fugacity in terms of complication?
For me, it's a formal variable.
What is it?
T is a formal variable. T.
What does it mean to say fugacity is equal to 11.1?
Okay, so you specify the density
Well, there is the intuitive idea of density of the gas, because the point is equivalent to put hexagon, and I have shown a picture last time when the hexagon are very packed, the high density, then they're all blue, or all red, or all green. So but from our computer view, T is just a formal variable, which is counting number of hexagons in the pyramid. I don't know the relation with physics, but at least.
No, but it is here. And
Yes.
Rho is a function of
Yes.
T. If you're given rho, you want to say it.
Yes.
Or the other way around. So give me a T, I'll give you a N.
Mm-hmm. But for me, see,
Yeah, this is the row S.
because you.
Activity row S.
Usually in Ising model, T is a capital T, the temperature, which become T, formal variable, number of edges of some configuration.
So fugacity is like related to density by this.
Yes, yes.
So, in fact, yeah, T d by dt is d by d mu, which is the chemical potential. So, they're related by exponential.
So if you know rho of T, then you can deduce the Z of T. But the interpretation, commutative interpretation, is in terms of rho of T. So again, we are going to take the thermodynamical limit to understand what it means in 2 dimensions. So you take the logarithm of this polynomial power 1 over D, which is 1 over number element in D, logarithm of the partition function, and by logarithmic lemma. This is good to take the inverse. Instead of staying at the floor level with polynomial, if I take the inverse of this, I am going to have the derivative function for Heaps. And the inverse, logarithm of the inverse, is just a minus the logarithm. So I can get by the logarithmic lemma that this expression, in fact, is 1 over D, P index D. So this is a derivative function for pyramids of hexagon on the domain D, up to the sign, it's minus T, derivative of the inverse of Z, and replace T by minus T. To get the derivative function of trivial Heaps, to get the alternating derivative function of trivial Heaps, so the inverse will be Heaps. Taking T times the derivative will give me the pyramids. And with this change of variable, I have to, this is a derivative function for pyramid of hexagon on D. And again, I have to take the mean of all derivative function for all pyramid in the domain D. So I did not give the complete proof, explicit proof, but you can do in exercise. The theorem I state, if you take, I can define the limit of a domain. Usually physicists take rectangle, but here I can take any domain. You fix a number k, for a fixed k, then you have a certain border of the domain. This count all the point, which the distance to the border is less or equal to k. And then if the domain D go to infinity, such that for any fixed k, the area of this domain divided by total area go to 0. So the area of this domain is going to be, of this border of the domain is go to 0 compared to the total area. Then I claim that the derivative function for this all pyramids in the domain, this is going to turn to the derivative function for pyramids without any condition on the border. It's exactly the same calculus in 1 dimension. I did not give in the class, but you can check by technical detail that this theorem I stated last time is true. And so I state that minus rho minus T, the density of the hard hexagonal model, is exactly the derivative function for number of pyramids on the triangular lattice with n hexagon up to translation. When I am counting pyramids on this hexagonal lattice, or triangular lattice, it's of course up to translation.
But this formula is valid for any lattice, not?
Any, yes, I can do this to any lattice, yes. Even the Ising model, you have to count this, what they call closed graph, is graph on a rectangle such that in any vertex there is 0, 2, or 4 edges arriving, and then the thermodynamical limit is going to be pyramid of such a closed graph. It's exactly the same reasoning. So from the commutative point of view, it's better to work with these heaps of pieces instead of working at the floor level, because you have to give an explicit formula for this polynomial. In the Ising model, it's possible. You have a Pfaffian, etc., for a given rectangle. But for the hard hexagonal model, if you take a rectangle, there is no formula for the number of ways to put this hexagon 2 by 2 disjoint. So if you want to work at the commutative level, it's better to go above, after the thermodynamical limit, and then I have something much more easy to handle. And this is so the pyramid of hexagon. And I finished the class last time by asking to explain the algebraicity of hard hexagon. So now I explain more than what I said last time. So this is a research project, but be careful. You know, in Stanley or in the book, sometimes the exercise are from 1 to 5. 4 is very difficult. 5 is open. 5 minus, it's conjecture, but easy to solve. 5, it's conjecture. 5 plus is very difficult. Here I put 5 plus plus plus. So if you are going to a thesis, don't do that. Don't go on this problem. I have been looking for 30 years. I never managed to. So proof directly means that without, if you go through the Baxter, of course, if you go through all this Baxter solution, so he puts the gas model on the triangular lattice with 2 parameters, L and M, satisfying some conditions so that the transition matrix to LM and L prime M prime commute. Then he can solve the model, and the hard hexagonal model is a special case, a limit case. If you are on a square lattice, then this also another limit case, but it's not on the variety where you can solve the model. So there is no hope to solve the hard square lattice model with this solution of Baxter. So it may be very interesting to see if you can make pyramids on a square lattice. Is it algebraic? We don't know. Is a solution bijection for hard hexagonal on the triangular lattice maybe can solve the hard square lattice? I don't know.
Has anybody computed AN?
But it's difficult. So I give to some students in Australia, but they get 40 or 50 first term, and it's not enough to see if it's algebraic or not. Because the algebraic equation for hard hexagonal, it's about its big equation of degree 12. But from I show you the solution of the hard hexagonal model with Roger-Ramanujan identities. From this, you can deduce, you can give a proof that it's algebraic. So I'm going to show you the system. So prove directly, without going through the machinery of Baxter, because this is a simple commutative problem. What is the number of a pyramid of hexagon? Show it's the derivative function is algebraic. So you have to show, the research project is to show that it's a solution of the following algebraic system of equation. Here is a system of equation. So it's very nice, you see. First equation, y equal 1 plus t y2. Oh, if I cancel this, I would have Catalan numbers. But I have an extra term, it's dig path with you can jump at level -2. An extra step. Now you put f equal t2 y to power 5. And then g equal 1 plus 3 f g2 minus this term in f and g of degree 4. So now you put h equal t g y3. And I claim that minus 1 minus 2, the generative function of pyramid is h over 1 minus h. So h is primitive pyramid. Primitive means there is only, below the maximal hexagon, there is only one hexagon. If there is the maximal piece, that's all. So h is primitive pyramid of hexagon. Any pyramid of hexagon is a product, is a sequence of primitive pyramids. So you see, it looks nice, this algebraic system of equation. Because if you go the physics paper, there is some equation of degree 12 with coefficient, a terrible coefficient polynomial in T. But if this system was given to me by Deepak Dar, who has colleague in Tata in Mumbai, from the equation, the Q series of Ramanujan, etc. They deduce this algebraic system of equation.
Highest degree is 3.
Here in G we have 4. Yes, F. You see it's.
6.
So you see F. This term is a product of y can be this or this. So this term is a product of the two terms here, T2 y5. So this is Catalan plus a variation more complicated than Catalan, right? There is a term in y3.
So you will explain what each step counts?
No, I have no idea.
Research project.
Research project, 5 plus plus plus. Be careful. For your student, don't give this to your student.
But what each intermediate step
Yes,
counts
yes.
maybe?
I try, but I never succeed.
Oh, you're saying if we find out what each step counts, then we'll have solved your 5 plus plus plus.
No, to explain, show.
Projection.
No, the problem is, I give you pyramid of hexagon, show that geometric function is solution of this system of equation.
So firstly, we figure out what y counts.
Yes. So y is easy to interpret combinatorially. It can be dig path. You can go up, down, or down twice. Instead of going to level -1, you go -2. It can be this, but something different. You can make something different.
Then F is
But then the idea I have is you look this equation. It's 1 plus 3 square minus something degree 4. So this reminds me something on rooted planar maps. The class last year, rooted planar maps, I explained all this, and its solution is algebraic, and look the system of equation. Here you have something counted by 3 times Catalan, 3 power n Cn, this h, and now you have h minus something of degree 3. This is a good tree, this is a bad tree. Of course, this is very simple. This is you see, rooted planar maps. And here I have, this is a good one minus the bad one. So maybe I try to get some inspiration from all the projection on planar maps, everything. So maybe you have to go through the heaps of hexagon and project on the maps. I don't know. This is an idea that there is something analog to planar, the generating function algebraic of planar maps. But it's very, and if you find an explanation, so go to the square lattice. Because if somebody asks me what is the pyramid on the triangular lattice, I say it's too complicated. It's better to go to the square lattice. It should be more simple. But nobody knows if it's nobody knows if it's algebraic. There is no equation at all. No solution in the gas model.
The first 50 terms.
Or some student. A long time ago, Conway, he was a student of Gutmann, I think. Gutmann student, and a long time ago, 20 years ago, maybe.
I think now he's a
Yes.
professor.
And I think Gutmann told me, oh, it's a fourth term, we cannot say if it's algebraic or not. Long time ago, because solution of hard hexagonal model was by Baxter in 1980, so 36 years ago. And I was doing Heaps in 85, so I start immediately to try to solve to explain this. So 30 years ago, I try and I give this problem to different, not to be careful to give this to young students. Okay, now today, second part of the chapter on relation with Heaps and physics about Lorentz, and we are going to work on Lorentzian triangulation in quantum gravity. So first, a very brief introduction to quantum gravity. You don't need to know anything on quantum gravity. So but let's go 200 years of physics or 2,000 years of physics. So the classical physics, Galilei, Kepler, Newton, this is classical geometry, Euclidean geometry, classical mechanics. This go back the geometry here, it's go back to the Greek Euclidean geometry. Okay, now we go to the 20th century, then come Einstein and the theory of general relativity, where you have to join space and time, and when you have a mass like this, the space-time is the curvature of the space-time. The mass reacts on the space-time, and space-time reacts to the mass. So this is a pictorial image you have seen maybe many times about the curved space-time curved by a mass. And you can see with your eyes, you see this is a Hubble telescope. This is a big cluster of galaxies. And behind there is another galaxy which is here in blue all around, because this galaxy, the light is there's a deviation by the mass of the cluster of galaxies. So the deviation, so you can see with your eyes the curve, the space-time is curved. This galaxy is the same galaxy appearing all around in blue. Multiple image of this image. You can really see that the space is curved. Maybe not the space-time, but at least the light is go in the geodesic of this space-time. So this is general relativity to explain the universe, black hole, everything. Now we go to the quantum mechanics, to the world of atoms. This is the quantum world. There is a totally different mechanics, the quantum mechanics. So there is two big theories in the 20th century. Quantum mechanics for the infinity small and general relativity for the infinity big. And quantum gravity means to unify the two theories, which are totally incompatible. The point of view is totally different in relativity in quantum world. So there is no way to put them together. So if you want to put them together, it's the same problem as to unify the four forces, fundamental forces of the universe. See, there's a gravity, And these three forces has been unified, the unified theory, the standard model. There is the electromagnetism, the weak interaction, the strong interaction. This is the three forces of the universe, but it has not been unified with gravity. So gravity is going to compete with electromagnetism at a distance, the Planck distance, which is 10 minus power 3, 31 or 32. So it's much smaller than the atomic world. So quantum gravity works at a very, very small scale, much more smaller than the atomic scale. When gravity and electromagnetism are in competition. So in quantum gravity, people talk about the form of space-time. There is some like the waves, the form, like the soap, and they will talk about baby universe. Some universe are born and another universe. So since 30 years, this is the Saint Graal of physicists to try to have a unique theory, and there is different candidates to unify everything, the theory of everything, what they say. So one candidate is the string theory. String theory, it's a very, we have here a specialist of string theory. So you suppose particles are like strings, open or closed, and the different vibration of the particle of the string give you all the different particles. So you can see some diagram like this. Instead of particle, you see this is a particle like point, but if you have string, they move in the like this. Or you can see picture like this, the quantic Calabi-Yau manifold, or here open string attached to a pair of D branes. So all this is very high-level mathematics, and for me, I am lost in string theory, and it's not my philosophy. Sorry, but because you suppose the world is continuum, these strings. But for me, the world, the basic components are discrete. For me, I prefer, being a combinatorist, to start with a discrete. Also, there is a non-commutative geometry of Alan Cohn. This is also a candidate to have for all this. He explained the Higgs boson. He can find it from this theory. So there is different candidates, starting from the fact that at the basic element, for example, there is some particle of space-time. Then there is some theory in physics that say that at the fundamental level, the world is discrete. We are moving on a lattice, and between the point of the lattice, there is nothing. We are moving, and so one possible discrete approach is the so-called loop quantum gravity. So Carlo Rovelli is one of the leaders, and many other people also. Loop quantum gravity, there are many people. You suppose at the fundamental level, the space is made of loops, and you don't need to. He has written some provocative book like this in French. The title is "And if the time does not exist." You suppose time is an illusion; it does not exist, and it's called un peu de science subversive, little provocative science to say maybe the time does not exist. And the second approach, which is much less known, is the causal set by Raphael Sorkin. So I suppose at the Planck level, the space-time is like this. So the point is space-time events, and you have a poset. And when you follow chain in this poset, this is the assay diagram, then you have the causal relation between different events. So you see there is different times when you follow the chain. And they like to say that this formula that when you put the partial order plus some number of points, this gives you the geometry. The problem is to embed this point, all these points and chain, in a Lorentzian manifold so that it preserves the causality. It's, but I should write to Raphael Sorkin because it fits very well with the Heaps theory. Because he's adding points in the poset, deleting. So once you have a poset, you know it can be realized as a heaps of pieces. And when it's a heaps, then you have many other poset. So in fact, you can connect the point. You know how to grow the poset once you are on a heap. So you have an infinite number of posets. So it should be maybe useful to revisit this approach with heaps of pieces. Is a student? Yes. In IIT. Oh. 5 o'clock next week.
Yeah.
Oh, I will be in France. I am leaving Sunday. Who is the name of the student?
Sumati.
Sumati?
Surya.
Because there is a write out. He has different students with different theses.
In the physics. We should talk about this.
So another approach, it's called CDT, causal dynamical triangulation. So this is also a discrete, you suppose the space is discrete. And this is what we are going to do today, because it's strongly related with heaps of pieces. So I did not know anything about quantum gravity or this causal dynamical triangulation, but my friend in Tata Bombay, he told me, Xavier, you should have a look at this paper, please. Look at this paper. So let's have a look at this paper. This paper was in 98 by Ambjörn and Loll about non-perturbative Lorentzian quantum gravity and topology change in nuclear physics. So I never go in a paper in nuclear physics. So these two people with another people, Jurkiewicz, they have written a survey paper in American, Scientific American, which are translated in French in the analog of Scientific American, which is Pour la science in French, and you see that the quantum, l'univers quantique auto-organisé, the quantum universe is self-organized. So if you look at this paper, I have a look on page 5. In quantum gravity, we are instructed to sum over all geometry connected, say, two special boundary of length L1 and L2 with the weight of each geometry G given by this. And lambda, the cosmologic constant. So when I read this paper, I did not understand nothing. And then page 7. Oh, Ft equals this, with F equals this. And this is a generating function of Catalan numbers. So I say, okay, he's right. I should understand and read this paper. Why the Catalan numbers are appearing in this 2D Lorentzian gravity? So another paper appeared by Di Francesco Gitter in CEA Saclay in France, and Christian Chen, is in, I think, in the Bohr Institute, and integrable 2D Lorentzian geometry and random walks. So this is a relation with Dick path. So we are going to understand this with maybe Dick path or heaps of diamonds. So definition. The 2D Lorentzian triangulation. What is a 2D Lorentzian triangulation? So Lorentzian means you separate time and space. Time and space do not play the same role as in Euclidean is in 2 dimensions. There is no difference between time and space. And then a little quantum, there is some quantum fluctuation, means there is some yellow triangle appearing by random. And when you have some yellow triangle like this, you see, then you squeeze, you delete these two edges are going to be touched. So you get this kind of thing after random fluctuation. This is the intuitive idea, but let's say the precise definition. No, so this is a Lorentzian triangulation. So this is the cometal object you have to study. So you see, you have some strip, a sequence of strip. Each strip is each red line is a constant time, time 0, time 1, time 2, time 3. And in each strip, you see there is a sequence of triangle, which maybe are down or maybe up. So this is a definition of a Lorentzian triangulation. So you can describe, you see, it's so any triangle, you have a sequence of a triangle, and then from one strip to another, the triangle are joined, you see, here by an edge, here they just touched by a point.
Will the number of points on each time slice be the same?
Well, it can be variable. It can be, there is any number of strips, and on each strip, the number of black points can be vary from. So each strip, it's a constant time, it's a space. The space is one dimension, so it's very poor geometry. One dimension for the space and one dimension for the time. But at least it can be solvable. If you want to try to have space with 2 dimensions, it's much more difficult, much more complicated, but you will see at the end that it's possible also to say something. So what is the Lorentzian and Euclidean? So Lorentzian gravity means, you see there is in quantum mechanics, in relativity, there is signature. In the 4-dimensional space-time, it's plus, 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 minus for the time. The Lorentzian space, because it's minus the time. But Euclidean is you put a plus instead of minus. So this would be 2D Euclidean triangulation. In 2 dimensions, Euclidean, you don't distinguish time and space. So this would be Euclidean triangulation. But Lorentzian triangulation, you see, it's this. You really have a distinction between time and space. This is Lorentz and Lorentzian quantum gravity. So in this theory, there is no baby universe. because from such triangulation you can maybe add some new universe to this strip of triangle, but here we will cancel no baby universe. And the problem, what they call the path integral amplitude from the propagation, for the propagation from geometry L1 to L2. Here geometry L1 is the number of points here. L2 is the number of points on the top row. And this is a propagation of the geometry from a space with L1 point to a space with L2 point. The distance L, capital L is the number of strips, and G is a variable, there is a G for each triangle. So the commutative problem is to count such Lorentzian triangulation by the number, by the G, the variable G, number of triangle, the number of strips, number of points at the beginning, and number of points at the end. That's the 4 variable. So this is a very difficult problem if you want to count this in general. But as usual in physics, they do this on a circular strip. So you put your Lorentzian triangulation on a cylinder, and suppose you fix a point on the lower circle, and then you can cut your cylinder. Each time you see you go you follow the rightmost of there is different triangle here. You follow the edges of the rightmost triangle. Each time, if the point, you say when you have a point, is there is many triangle starting from this point, then you go to the rightmost edges of the triangle. So you can cut your cylinder, and what you get is this special Lorentzian triangulation. So the condition on the board, the left border, is that any triangle is up, you see. So this is the problem they'll solve in the 2 papers by these 5 physicists I showed you before. They solve the enumeration of this configuration with this border condition. In the second paper also, they solve also, if you have 2 border conditions, one every triangle up, and here every triangle down. Okay, so where is the catalog number here? So it's very easy. There is a bijection, easy bijection between heaps of dimers and Lorentzian triangulation. First. So here is a heaps of dimers on the integer. So here is a bijection. You replace each dimers, you replace by a pair of 2 triangles. So each dimers you. So in dot line, you see, I have my, it's going to be the support of the Lorentzian triangulation. So each dimer, you see, it's a pair of 2 triangles which touch by an edge. And then you see I have my dot line, so I have some strip. In this strip, see, there is 2 triangles. You are going to push the triangle so that all the edges touch together. And so in this, see, these 2 triangles are becoming this. See, these 2 triangles, I have 2 triangles going to the right, 1 triangle going to the left. So if I glue them together, I have 2 triangles going to the right and 1 triangle going to the left. See here, I have in this strip, I have this triangle going to the right, to the left. So you see, in each strip, you have this sequence of triangle on the top level for the hips. And then there is some triangle going to the right, some triangle going to the left. So you glue them together by just press them so that they glue together, and you get this picture.
Where is time in this?
Time is a red line. So if you want to go back, so I delete this to go back, and then I turn 90 degrees, and then I get my Lorentzian triangulation. Now reverse bijection, take this is very simple Lorentzian triangulation. The time, the red line are constant time. In each strip there is some sequence of up or down triangle. So I rotate it, I add, everywhere I add all, I join, if there is many points here, L1 point here, L2 point here, I join all of the points here to get a single point here, and then you replace now, you see, you replace each pair of triangles which are connected by a vertical edge, you replace them by a dimers. It's kind of dual map, you see. It's a dual map, and then you see your dimers, the hips is appearing. If you connect all these black points in a single vertical line, you get a heaps of dimers. Is it clear? It's a You see, for example, in my heap, if I take this sequence of dimers, one dimer is going to the left. So it's a sequence of half edges. One is going to the left, right. So I get above one triangle to the left, one triangle to the right, one triangle to the right. If you look carefully on each vertical line of the heaps of dimers, if you look carefully, then you have a sequence of dimers going to the left or the right. So you have a word in 2 letters, and then you replace this by a word triangle going to the left or to the right. And then the triangle are going to join together by a vertical edge because of the heaps of dimers. Look carefully at this picture and you will understand the bijection. So it's an easy bijection. It's no problem. It's kind of dual map, but in special case of this Lorentzian triangulation. So now I can get my gyrating function. My 5-parameter gyrating function for this kind of Lorentzian triangulation. So what means the 4-parameter means you have to count such Lorentzian triangulation with the parameter number of points on the for t equals 0, the time 0 for the bottom line, number of points at the upper line, number of triangle, and number of strip. So if I look again my bijection between heaps of dimers and Lorentzian triangulation, in the case of the Lorentzian triangulation with the border condition on the left, so this, in the case of the special case of Lorentzian triangulation, and then you can easily see that the bijection is in bijection with pyramid of dimers. And you have to, if you rotate this picture 90 degrees, you have a sequence of a yellow triangle which are going always with looking to the right, and this is going to give you a sequence of dimers which covers the whole heaps. This means it's a pyramid, in fact. In fact, a semi-pyramid. Semi-pyramid means the maximal piece. You have a pyramid, the maximal piece of the pyramid is here. It's on the first column. So you have a bijection between this and semi-pyramid of dimers on a segment. So the length of the segment, the v, the variable v, the length of the segment is going to be the number of strip. You see, number of strip, if you turn 90 degrees the picture, it's going to be the number of column. Now you have to count by the number of points below and one number of points above. So you have to count how number of touching the dimer are touching the first column. So number of dimer in the first column and number of dimer in the last column. And then number of triangle is going to be related to the number of dimers. Each dimers count for 2 triangles except the extreme dimers, but you can easily, because the extreme dimer I have added here is the number of triangle I have added, it's exactly the number of points on the first and second row. So it's equivalent to count semi-pyramids. The problem is equivalent to count semi-pyramids by the number of dimers, by the width, semi-pyramid in the finite width. So the variable v, which can't use the width of here the width is n. Variable v counts the width of the pyramid. Variable t counts the number of dimers. Variable y and x counts the number of contacts at the border of the pyramid, which is number of contacts at the border, upper border and lower border of the triangulation. And so exercise proof that the gyrating function, first with only 3 variables, because this was already known, the gyrating function q of t, y, and v with only 3 parameters, where t is the number of dimers, v is the width, y is the number of dimers touching the first column. So the gyrating function for this 3-variable pyramid, which gives you the Lorentzian triangulation with 3 parameters, is given by this very simple gyrating function. It's the sum over all n of y t power n v power n divided by the product of this modified Fibonacci polynomial. So the fn tilde modify Fibonacci means I introduce a variable y inside. So y fn tilde is going to be defined by this recurrence relation, and fn is a Fibonacci number polynomial. Remember the Fibonacci polynomial, you are counting how many dimers you put on this finite segment, and then the variable y is going to count how many times you touch the vertical axis. So it means how many times you use the dimer is going to be 0, 1. And so this gives you this recurrence relation. If you have a trivial heaps of dimers, then maybe the it's there is no dimers touching the origin, so this gives you this Fibonacci polynomial. And maybe there is a dimer touching the origin, so this gives you the variable y, which counts the number of time you touch. And then what remains is only classical Fibonacci. So it's just a modification of Fibonacci to take account how many times you are going to take the first dimer to be 0, 1. But so this is not too difficult, but exercise to prove that, in fact, this is a generating function, is the inverse a product of two Fibonacci, Fn and then Fn plus 1 modified. So I give you a hint to this to solve this exercise. Use the bijection between disk path and pyramids of dimers. So when you have a disk path, you see it's then the time you touch, this is going to be the parameter y. But the main thing is to understand why there is inverse of product of two Fibonacci. Modify with the y, but put y equal 1 and try to solve first without the y. So the idea, maybe I give you the hint, more hints, it's when you take a disk path like this, take the first time you are touching, because the disk path must touch a level, it must touch this level. The pyramid is, the width is n, means the disk path is bounded by n, but it's touching the level n. It's touching this. So you just take the first time you touch, and then you can cut your path in two different paths, and then each part of this path is going to give you inverse of Fibonacci Fn and inverse of Fibonacci n plus 1. So I don't say more because I am solving the exercise. Maybe there is a direct proof with using movement pyramid without disk path, but maybe the most simple is to cut your disk path in two parts, and each part is going to give you the inverse of this Fibonacci. So once you solve this exercise, it's not too much difficult to introduce the parameter x, number of times you touch the rightmost column. So it's going to be Fibonacci polynomial with two variables x and y. So y is counting when you use the first dimer 0, 1, and x counting the last dimer n minus 1 n. And then proposition, the generating function for semi-pyramid with the 4 parameters. So again, it's the same as before. There is one extra variable x here. I claim this is exactly this. Then there is two proofs. The first proof is given by this drawing. So you have a pyramid of width n. So there is some dimer here at the last column. Take the topmost of the last of the dimer. You push. You get an ideal for the order relation, the poset related to the heap. So you get a pyramid in the reverse way, in the left way. So in green, the green part is given by this polynomial. Is the same as before, the same as this proposition, but with the extra variable x. By the way, this proposition was given in the paper in 2012 by Mireille Bousquet-Melou and Reschnitzer. We will see after, at the end of the class, that in fact they did not know. They were doing Lorentzian gravity in a two-dimensional. They were working with multi-dimensional animal, some extension of directed animal, and I will discuss this after. So I just apply this Mireille Bousquet-Melou Reschnitzer formula, but with the x variable x, and multiply by the blue part. The blue part is again the same. So the blue part is the generating function for pyramids, which is the ratio of the numerator by denominator. So this is easy, just application of the inversion lemma, and this polynomial cancel, and you get this. So this is a possible proof, just one extra variable x, and it's easy to prove like this from the first formula. There is an interesting second proof, is another decomposition of the pyramid of dimers. It's like this. So I have a pyramid of dimers. Take the lowest dimers in the last column and push above. So in blue, you get what I call a double semi-pyramid. It's only one maximal piece in the first column and only one minimal piece in the last column. And double semi-pyramid, generative function is going to be this. I will give you an idea of the proof. And the green part is any heaps of dimers on the segment 0 and minus 1. So this is the inverse of this modified Fibonacci. This is just Heaps, inverse of trivial Heaps with the modification of the two border of the parameter y. So this is easy, but why? This is a derivative function for double semi-pyramids. So it's interesting because double semi-pyramid is exactly in bijection with this triangulation, which were considered by Di Francesco and the co-author in the second paper I show you. They have this special case of triangulation. And I claim proposition that the derivative function for double semi-pyramids is exactly given by this, which is the derivative function for general heaps, up to modification of a numerator. But in fact, it's true that there is a bijection between double semi-pyramids and general heaps on 0n. So I claim that this double semi-pyramid in bijection with the general heaps. But when you go from this to this, you are losing some number of dimers. If the pyramid have t power m dimers, then the heap has the number of dimers m minus n. So exercise or proposition how to prove that the double semi-pyramid is exactly in bijection with heaps of dimers. If you prove this, then you have this formula. This is a formula for the double semi-pyramid with modified with the y and the x each time you touch the border. In fact, it's consequence of the general bijection. See, if you take a path like this, like a dig path, but you start from this, and then you finish here. If you apply the classical bijection between paths and heaps of dimer, what you get is a self-avoiding walk going from U to V. It's going to be exactly a big segment going from 0 to n. And below, you have some heaps of dimers, such as that the maximal piece must touch the self-avoiding walk. But self-avoiding walk is covering everybody. So there is no condition on the heaps of dimers below. So this gives you the general heaps, the bijection between such a path, like this, going from this to this, and a pair. You are losing all the dimer corresponding to the self-avoiding walk, and below there is a general heaps. Now from this, how to get a semi-pyramid? In fact, I take another path, starting from 0. I go straight to n here, and then I go back in the reverse direction on this path. So some dimer is going to fall down, and what I get is exactly the semi-pyramid. So you are reading your path in two different directions, and this is the heaps you get when you read your path in a reverse direction, using again the classical bijection. And this is a proof that there is a bijection between general heaps and semi-pyramid, and this is a proof of this formula here, which gives you another proof of this, which is this is the first proof, and this is second proof. But you see, we are playing. The interest is because this triangulation has been considered by physicists, and it's in bijection with general heaps. But you are losing up to the t power, the number of dimers you are losing in a self-avoiding path going from 0 to n. Now the space-time there is a curvature. The mass is give a curvature. So the physicists introduce a parameter curvature in the space-time. So here, when you are working in this, the space-time is flat, completely flat. In each point, above the point, there is a 3 triangle. There's 2 blue lines, and below there is 3 triangles. So intuitively, there is a curve. Space-time is a high curvature as the number of triangles you have above. If you have I triangle, if you have J triangle below, so if I equals 3, I is always more equal to 3. More equal than 3. So if you take the I minus 3 plus J minus 3, this gives you a parameter A, which measures the curvature at the point, at the vertex, which is here. And I will define, this is the upper curvature and the lower curvature. For example, here, the upper curvature is there is a 4 triangles, so there is one, the parameter A, there is 2 triangles touching, and here parameter B, B, and B for each for each of these. Here b equal parameter 2, and here is 1. Total curvature is 3 for this point. When it's flat, when there is no, it's 0 curvature. And in the projection with the heaps of dimers, then what happened? You see here, these two triangles, there are going to be two starting of dimers. Here there will be full dimers here, and here there is 3 dimers. If you turn to have a better understanding with the heaps of dimers, so you see here in this point, what happened is that I have 2 dimers here, such that they are maybe they are not touching, maybe there is a dimer between the two, but if you just look this point and what happened to the right, there is no point between this and this. Or here it says there is no point. If you look the vertical line between these 2 vertices, there is no other point. So this means there is, and they are oriented to the left or to the right. So this means there is a curvature, up curvature is here, up curvature, left curvature is here, the down curvature. So it's a number of times, 2 dimers, the half part of the dimer, there is nobody between them.
So no curvature just means that it's nice.
Yes, it's a nice. So here is an example. Here is a heaps of dimers. General heaps of dimer, I don't consider them. Now I take general heaps of dimer, not necessarily the one giving the special condition on the left border or the right border, so that it's a Catalan number. And now I am using the stair decomposition. So the stair decomposition is very useful for the curvature. It's a surprise that take the stair decomposition. And now I can read the upper curvature. You see, look, here there is two points. The dimer are oriented to the right, and there is nobody between these 2 points. So you have a parameter A, the upper curvature. Here also, there is nobody between these 2 points. But if you take any other point, this is the only pair of vertices in the dimer, such that there is nobody between the dimer are oriented to the right. This is the upper curvature, and there is nobody on this vertical line between these 2 black points. Now the lower curvature, I claim I have 3 times the B. So here, these 2 points, there is nobody between them, and the half dimer are going to the left. So you have 3 times this configuration, which means I have a curvature B3. So the whole triangulation, Laurentian, that's the only pair which appear. There is no other pair. You have to find a pair of 2 vertices, nothing between the 2 vertices, and the 2 dimers are maybe oriented both to the left or both to the right. Look, if you take these 2 vertices, one dimer is go to the right, one dimer go to the left. If you are on the flat space, if you look at in vertical line, dimer will alternate right, left, right, left, right, left. This is a flat space where they constantly alternate between right and left. Each time there is twice or many times dimers oriented to the right with nobody between them. This gives you the curvature parameter. Amri, you seem thinking or skeptical.
To see what it has to do with the stair.
What is that to do with the stair decomposition?
How to count.
How to count. Now comes the counting with the stair decomposition. You see, it's because when you have this configuration with nothing between the two, this means that this dimer is the starting of a stair. Because you cannot put this dimer, any dimer belong to a certain stair of the stair decomposition, and these dimers in the stair, there is nobody above, because it would be like this, you see. If there is nobody, this dimer is the starting of a stair. And now here, this dimer is the end of a stair. Each time you have the B, means you are finishing, you are adding a stair in the stair decomposition. So A and B are only located at the starting of the stair decomposition for the A, and B at the last point of the stair decomposition, but not everywhere. Here you have many starting here. This one, there is no curvature. So what is the characterization? Characterization is the following. So put in green the left point of the starting of the stair, put in purple the last point of the dimer at the end of the stair, and put some light coming from above. All these green points, you see, there is, if you put some light, there is nobody above them at this point. But here, at this point, if you put the light, you don't see him. You don't see it. The light is not, it is in the shadow of all the light above. So these 2 points, this green point, they are hidden by somebody above them. That's the characterization. It's the first point of the stair, such that there is somebody above him. And there is only 2 of such points. All the other starting points, there is nobody above them. And dually same for the last point. You see, if you put some light below, then these 3 purple points, they are the only one which are the last point of a stair, and you cannot see them from below. So that's the characterization of the upper and lower curvature. It's a stair which, such as that, the starting or ending point are hidden by somebody above. Now, if you go back to the one counted by Catalan number, everything, so maybe it's a little complicated to get back to the proof of the paper by the French people, but the paper, in fact, work with transition matrix. And I don't think clearly where is the enumeration with the 5 parameters of the curvature. They have transition matrix. Again, two possible transition matrix with the eigenvalue, the commute, everything, and then they go quickly to the continuum limit, where the Bessel function appear. Bessel will be the subject of the last course next Thursday. So Bessel is behind the picture. And in fact, you can go back to the bijection between stair decomposition and heaps of segment, and then this point here, you can put them on the heaps of segment. And now heaps of segment are in bijection with Lukasiewicz path, so you can more or less characterize them in terms of Dick path in bijection with Lukasiewicz path. There was an exercise, and there was some last year's chapter about the Catalan garden. So I will not insist on this, it's becoming too technical. But this is the idea, so you can have you have the 4 parameters plus the 2 parameter curvature, the 6 parameter of this, you can do it combinatorially. Now there's a funny result. What are the number of heaps of dimers on 0, such that the total curvature equals 0? When you have a flat space, you say there is a, but there is some heaps of dimer which are not totally in bijection with the flat space. So, but if the total curvature is 0, what is the number of such heaps of dimer? And only one of the 2 curvatures, up curvature equals 0. And it's very easy because it's a Catalan number. Total curvature equals 0, this is a Catalan number. And here, up curvature equals 0, this is n factorial. Why? It's because if there is no curvature, it means that all the first point of each stair are visible. And this means that the indices are increasing. Same below. So this is exactly what we have seen in chapter 6a. This is a fully commutative element of the Coxeter group. So if all the indices of the first dimers are increasing, this is exactly it means that that you see all this point, the left point, you see it in full light. Nobody is hidden. As soon as somebody is hidden, means the sequence here of green number is not increasing strictly. You are backward, and so if you have only one of the 2 sequences increasing, and not the 2 sequences increasing, then we have seen in page 86 about an exercise to show that if it's only increasing upper or lower, then the number of such heaps is n factorial. So you have a basis of the EK algebra, of the algebra of the symmetry group. So it's nice to translate in terms of curvature. N factorial is only half. One curvature, upper curvature is 0, and total curvature 0 means Catalan number. Okay, now I will go to something different. I will go to what about if I don't put the condition on the border? The left border with all the triangle up means Catalan number. So this is easy. We are in the Catalan world, or even the 2 conditions on left border, right border. We are in the double pyramid, which is again the same world of Heaps and Dick path and Catalan. All this is easy. But what about if you have no condition on the border? So if there is no condition on left and right border, there is still a formula for the total number of such Lorentzian triangulation. So if you get a general Lorentzian triangulation like this, you see it in general it can be decomposed. You have some articulation point when the two it's reduced to 1 point on each of the line. So you can decompose any Lorentzian triangulation by a sequence like this of Lorentzian triangulation with no no such point. Then if you take each of these components, then they are in bijection, such triangulation with no articulation point. That's what we want to enumerate. They are in bijection with connected heap of diamonds. So what is a connected heaps of diamonds? So the problem, the general problem to count Lorentzian triangulation with no border condition, it's equivalent to count connected heaps of diamonds. This is much more difficult than the Catalan numbers. Because the geometric function of such a thing is not algebraic. It is not definite. So usually when you go above the definite level, means this problem is not solvable. But here there is an explicit expression for the geometric function. I gave it already in when I was a general introduction to geometric function, rational, algebraic, definite, and an example of a non-definite geometric function. So first, definition of connected heaps of diamonds. Connected heaps means that well, you can say that there is no empty column. You have no column which is empty with some diamonds on the left and on the right. Or you can say, if you take the projection, take the, what I can say, no, if I take the projection of the vertex, maybe not connected. It's the vertex can project all on the segment 0n, but maybe it's not connected. So there is no empty column, except of course, the column on the left or column on the right. But inside there is no empty column. So for each of these columns, there is some diamonds above. For any pair I plus 1, there is some diamonds which project on I plus 1 for any pair between 0 and n minus 1. You have a segment 0n.
But left and right, I mean, it's given by the lexicographic, given by the ordering that you are giving on the basic pieces, right?
Oh, I don't need an ordering here. Right? On the basic piece, it's
maybe you can just define it as when you cannot write it as a product of two different.
Yes.
Without the.
Yes, that's a good definition of the. It cannot be a product of two different heaps, which commute between a heaps on the left, a heap on the right, and it's a product of the two, means a union, and they commute. If you have two heaps, H1, H2 equal H2, H1, it means that they are. You can define some heaps which are disconnected. You can define any heaps of diamonds. You can define the connected component of the heap. It's some block of diamonds which each heaps is going to commute with the other. Which means that in the two heaps, H1, H2, any diamonds of H1 is not in dependency of any diamonds of H2. So this is another definition. So this has already been introduced by Mireille Busquemelo and Rechnitzer in 2012, connected heaps of diamonds, because they want to get an extension of directed animal on the triangulated. They want to extend this to multi-directed animal. So this was your question, from a question, to put many source points in the animal, but not on compact size source point with a 45-degree line, to put some, you see here is a multi-directed animal with different source points. So I'm not going to define what is multi-directed animal, because they're in bijection with connected heaps of diamonds. They define this to have a wider class of directed animal, so that they're a bigger directed animal. You see, in general, it's conjectured that the total number of animals behave asymptotically like 4 power n. Mu power n something. Mu is supposed to be 4, but it's not exact. We don't know exactly. Maybe it's 4 plus epsilon. So they want to have a big class of animal, such that asymptotically the an is going to be mu power n minus a critical H1. And mu for directed animal is 3. General animal is 4, so they have multi-directed. It's between 3 and 4. It's bigger than 3. So they try to have to go to more and more general animal to try for the general problem of general animal. So they define this. It's a technical definition, you see, but from a connected heaps of diamonds like this, by pushing above, you can get a multi-directed animal with some source point. It's too technical. It's not. We don't need to define this. The main problem is to enumerate these connected heaps of dimers. So that's what they have done in their paper by using a lot of calculus and recurrence relation. And in their paper, they show that the diuretic function.
Source points are all the minimal points in the heap.
Yes, you see there is. First, yes, you take the leftmost minimum element, then what remains, the second one, and the third one, I think, yes. And then you transform this into an animal, directed animal. But what you have to retain from this is just we are interested in counting connected heaps of dimers. So let's Q denote the diuretic function for half pyramid. Oh, it's semi-pyramid, the same, semi or half pyramid, which means the diuretic function for Catalan numbers starting at n equal 1. So the non-empty pyramid, of course, pyramid is always non-empty, it has a maximal piece. And then in their paper in 2002, they give a diuretic function for connected heaps. This is a beautiful diuretic function. It's Q divided by 1 minus Q divided 1 minus 6, infinite power series in Q. So I remind you, Q is a diuretic function for Catalan numbers, starting with T plus 2, T2 plus, etc., with non-constant term. So I am going to give you a proof of this, a bijective proof. So in their paper, they show that this is not definite. Usually to show a diuretic function is not algebraic or not defined, you have to study the singularity of the diuretic function. But here is not a class on asymptotic or analytic combinatorics. It's just a class on enumeration, algebraic combinatorics with emphasis on bijection. So here there is a nice bijective proof. In fact, I will prove that if you allow me to replace this by this, a few lines of calculus, so in red, this is equal to this, then I will give you a bijective proof of this, which have been used. The interest is that it gives you a tool which you can use for other problems. And we will see it have been used to solve some open problem in a partially directed animal. So here is what I call the Nordic decomposition of a heaps of dimers. So here is a big heaps of dimers, and here is a Nordic decomposition. So first step, you take all the maximal piece, and here there is one, the other one, and you take the rightmost maximal piece. Okay, here it is. Take the rightmost maximal piece, and you push, you take the ideal below the maximal piece, you get in blue a pyramid. Pushing down, you get a pyramid. So remember, the heaps of dimers is connected. Now, if you delete the blue pyramid, what remains is maybe a disconnected heaps of dimers. See here, if I delete the blue pyramid, if you look carefully, this is empty column. And maybe there is another one somewhere. Yes, here there is an empty column. So you take the connected component. So here is one connected component. Here is in green, it's another connected component. So in green, the leftmost, I took the connected component, and in green, the leftmost connected component. I claim that because the full heaps is connected, so the green part must overlap the blue part. Suppose the green part was far away on the left, it would not be connected. So the green part is overlapping the blue pyramids. And what remains, you see, I have two other heaps here. So if you look at the right of this was an empty column. So I put in yellow. Just at the right of the green part, there is an empty column. And here there is just at the left of the maximal piece, this column must be empty. this yellow column. Because if it was not empty, this would not be a maximal piece in the total heaps. So you have two yellow strips, which are empty. Maybe there is nobody here. But at least you have these two yellow strips. And here is a distance. This is k minus 2. Total distance between this and this is k. Now the next step. Take this leftmost yellow column, which is empty, but there is a piece here. Maybe not. Maybe there is nobody. But maybe there is a piece. And you push it. Again, you get another pyramid. In purple. And then between the two yellow strips, here you get any heaps of diamonds. Here it's a general heaps of diamonds. But I have an integer k here, such that you see in blue, if I push, suppose you push down this purple pyramid. So what remains from the blue pyramids deleted when you delete the purple pyramids, what remains is a pyramid with a left width equal to k. You remember there was an exercise, prove that pyramid with a left width equal to k is q power k plus 1. Right? There was an exercise in the former chapter. Second part of the exercise was to show a relationship between Fibonacci and Catalan number. So I have this decomposition of my heaps in several pieces. There is the blue, the purple, the green, and the yellow part between the two yellow strips. So let's go back to the picture. So the blue minus the purple is q power k plus 1. I have an integer k. Between the two, this is a general ellipse on a segment of length k. So we know it's 1 over the Fibonacci numbers. And then this is any pyramid with no constraint on the width. So derivative function for general pyramids. It's, why is it q over 1 minus q? So here is the formula. We should read the formula. So any connected heaps, any connected heaps is the product here, C, is the connected heaps, multiplied by the general heaps on a segment of length k, multiplied by these two parts, the blue and the purple. So the blue, why is it q power k plus 1 divided by 1 minus q? This is a general heaps between the two yellow strips. This is the left component, the C, which is here, the C, which is here. This is 1 over Fibonacci k minus 1, because it's between the two yellow. This length is k minus 1. And the blue and purple part, it's q over 1 minus q multiplied by q power k.
That was the, yeah. Raised to k is,
Yeah, because this is a general pyramid which have length, the width is k equal 1, 2, 3, 4, 5, so it's q plus q2 plus q3 plus. It have any lower width, so general pyramid here is because q is a derivative function for pyramids, for semi-pyramids. Q, Catalan number, is derivative function for semi-pyramids. So derivative function for the purple pyramid, any pyramid has the width equal k equal 1, k equal 0, 1, 2, 3, 4, 5, etc. So the derivative function for the purple part of the heaps is q over 1 minus q. It can be q with left width 0 or 1 or 2 or 3, so it's q plus q2 plus q3 plus q4. So this is the purple part of the pyramid. This is the blue part. This is the general heaps, and this is the left component. And maybe this is there is no. Maybe the heaps is reduced. It's finished. There is no. It's reduced to the purple pyramid, and it's finished. There is no other component. So even you can play recursively, you see, because this is a recursive C equal C. So you can recursively, so this is a full Nordic decomposition. Now some people tell me, but what you are doing with Heaps is exactly equivalent to what can be done with commutation monoid. Heaps are equivalent to commutation, so why to introduce Heaps? Because everything can be done with word up to commutation. Okay, I say, okay, translate this in terms of commutation monoid. So translate this. So you see the power of the Heaps is the geometry that what you see is very natural to do this, and then you get this nice decomposition. But it would be very hard, I think, to do it only with word and commutation monoid. Of course, it's equivalent. The two theories are equivalent, but the interest of one theory is to have one of the theories you like word, which you go inside a finite automata, or if you like a spatial picture with the intuition from the gravity of the space. And when you do quantum gravity, it's natural to do diamonds which fall down on the ground and have some gravity. So from this equation, then you get immediately C equals this. But now this is not exactly the formula given by Mireille Bousquet-Melou and Reschnitzer, counting connected Heaps, which are in Bayesian with multi-directed animal. So you get this formula if you prove that replace Fn, there is a Fibonacci polynomial. If you want to have everything in terms of Q, then Fibonacci polynomial can be expressed in terms of the Catalan generating function. And in fact, I will prove this, which is equivalent to this. So the last part of the proof was an exercise in a former chapter to prove. So why I call this Nordic decomposition? It's because I was at a meeting in Iceland, the first Franco-Icelandic meeting. They call this Nordic meeting because it's a Scandinavian meeting, but it's connect Denmark, Sweden, Finland, Norway, and Iceland. So this was in Iceland in winter, in January. So I thought I found the bijection, but the bijection was not correct. I go back to Bordeaux, and then just after I go to meet Agleflair, again in winter, and then there was a beautiful, and then I correct the bijection. So the bijection was correct so this is why I call this the Nordic decomposition. Now to finish the proof, you have to connect the Fibonacci polynomial and the generating function, the Catalan number. Is there a class at 3:30 or it's 3:24? So 10 minutes? So let's call D equal 1 plus Q, the generative function for Catalan, including the 1. Fn, the nth Fibonacci number. Then the exercise in the former chapter was to prove this identity, which is equivalent to this one. D power n equal 1 over Fn multiplied 1 plus Q plus Q2 plus Qn. And so the first part of the exercise was to prove that if you have a pyramid with left width equal to K, the derivative function of such semi-pyramid with left width was equal to Q power K plus 1. If the left width is 0, then you get a Catalan number. But the general formula for pyramid with this, and here is the proof, you see. The pyramid with left width equal to K is exactly Q power K plus 1 because you just number the maximum, this diamonds, topmost diamond in each column, 1, 2, 3, 4, etc. You push the first one, second one, third one, and then you decompose your pyramid in K plus 1 distinct pyramid. Now, second part of the exercise was to prove this identity, to prove that this is the left part and the right part is the generating function for heaps of diamonds on the infinite line 0, infinite, such that the projection of the maximal piece are between 0 and n. The heaps can be very large, infinite, very big on the infinite line, but the maximal piece must be between 0 and n here in this. I claim the generating function for such heaps is this, or also equal to this. And the proof is given here. So to prove is d power n. Again, in each column, you push down from the first column, second column, third column, and then you extract a sequence of semi-pyramid, maybe anti-semi-pyramid, and you get d power n. Now the right part what I am going to do, say I am between on the segment 0n, I push in the last column. You push, maybe there is nobody, but if there is nobody, you don't do anything. If there is a diamond, you push, and what you get is a pyramid. But a pyramid of left width at most n. So this blue pyramid is 1 plus q plus etc. plus q power n. The lower width, the left width is at most n. Maybe empty. And what remains, the green part, is n heaps on 0 and -1, so it's 1 over Fn. So that's the proof, total proof of the Nordic decomposition. And the interest of such decomposition has been used in a recent paper by Axel Bachet in 2016. When the people 30 years ago introduced directed animal, there was also the partially directed animal. Instead of animal going to the only with the directed path going north or east, open problem was animal with 3 possible steps. Any point of the animal can be reached from the source point going north, east, or south. Or also diagonal step on a triangular lattice. So Bachet was able to solve this problem by putting in bijection such animal with heaps of segment and applying the methodology of the Nordic decomposition. So see, it can be useful to reprove some result which can be done by calculus, but to reprove them, and then you have a tool which you can solve open problem. And so you get everything, the enumeration, the asymptotic, everything. So it's a larger class of animal. And I will finish in 1 minute by extension in 3 dimensions. So this is very difficult. This has been done by students of LOL and in some theses. This is much more difficult. So you cannot do in 3 dimensions. It's very difficult. You can do special case 2.5, special case of Lorentzian triangulation. In special case, give you reduce the problem to heaps of segments with you see segments are connected blue and red, and so there is some extension of this again using heaps of pieces, and it's very difficult problem. Okay, so this is the end of this chapter. Thank you very much.